Folks, for this screencast, I want to talk about JagSAT-1, a 2U CubeSat that I have been working on for, well, me and numerous amounts of people. Dr. Spencer, Dr. Richardson, Dr. Latif, Dr. Russ, and myself. Most of the faculty are electrical engineering, and really I probably did 20% of this project, but I just want to talk about my side of the story. You take a look at this 2U CubeSat. Here's a really nice CAD rendering that that the mechanical engineering team worked on. Oh, and by the way, it wasn't just faculty. There were probably 40 or 50 students over the course of the last 5 years who have worked on this. And if you've been watching my channel for a while, you've noticed that I have been making a lot of videos about reaction wheel control and magnetorquer control and dynamics and everything like that. And it's basically been because of this project that we've been working on. And I mean, I don't know if you've seen this video, but I made this. Oh shoot, there's audio in that. Let me turn the audio off. I made this like pretty terrible simulation of a portal cube going around to Earth, but it was all because it was all to help with this project. And we looked at like GNC, and I did some sensor integration and things like that. The reason why I'm making this video is because we finally deployed. We actually got to space and deployed, and so I wanted to talk about everything that went into it. We made these really terrible, what's it called, 3D printed models. Here's the board stack and the comm boards and everything like that. And at the time, we actually were going to put 2 reaction wheels in here. I actually noticed those 2 reaction wheels there that we were planning on putting in there. And we ended up getting rid of them. The ConOps kind of changed. Doing reaction wheels on our first go was kind of difficult. So it's funny because there's actually this massive gap here in the CAD model because we removed the reaction wheels. But if I show you some of these photos, this is what's pretty cool about this project is that from start to finish, we've got that CAD model that I showed you. Here's like the outside with the solar panels. Here's the inside, the cutaway, showing the different board stacks and everything like that. And then, we go to fabrication and, we made some 3D printed models just to make sure everything fit in until finally, here's a photo of the board stack actually outside the CubeSat. And Dr. Russ was instrumental in writing 10,000 lines of code, I think he said, or more. I helped with the Git version client to make sure everything was properly oriented, and I did write probably 20% of the ADCS flight hardware or flight software. Sorry, but Dr. Russ, he not only did he write all of the flight software of the entire board, but he also wrote the other 80% of the flight software. So I just wrote a couple functions here and there in C and tested them, in some software in the loop simulation. But so here's a picture of the board stack outside the board. And then here's Dr. Spencer, and hopefully he won't get mad for me showing him a photo. So this is our clean room. So they built, some 2x4s and put up some plexiglass, and we had a pretty nice HEPA filter. And so here's the board being, the satellite being put together. And then here's the photo where it's right before it is delivered to NASA and deployed from the NanoRacks deployment mechanism. And so the way that we got a ride was we got on board a rocket and got pushed out to the International Space Station, and then on September 6th, here's a photo from Jessica Watkins. So NASA took these photos. So this is courtesy of NASA. Thanks Sarah for taking these photos, and thanks Jessica Watkins aboard the ISS for taking these photos. And so there's the NanoRacks deployer right there. And so I'm just going to kind of page through these photos, and you'll see, there you go. There are the CubeSats coming out. And what I think is interesting is 3 CubeSats came out at once. And so there is one in the front, and then there's JagSat-1 right there. And then here's a 1U CubeSat right behind it. What I think is interesting is that, the inertia of this CubeSat here is a lot smaller. And so it actually tumbles quite a bit. You can actually see that as it's moving along. It's not even, I don't know how many seconds are between these photos, but it definitely tumbles quite a bit versus, say the JagSat CubeSat is not detumbling very much at all. Now, what they told us was, so this is where, I sort of had to help a little bit more, is that we needed to figure out how to communicate with our satellites. So the ConOps says that after JagSat is deployed from the NanoRacks deployer, the orbit is at 422 kilometers ish, and so the orbit's around an hour and a half. Now that means you theoretically could communicate with the satellite every hour and a half. The problem is the inclination of the orbit is 51.6 degrees, and the Earth orbits underneath it, every 24 hours. So you really only get around 2 passes a day, or once a day, just depending on the elevation that it goes across the sky when it flies across you. And so the Dr. Russ, again, being very instrumental, started putting together, and let me see if I can get this ground station photo, started putting together this ground station. So I was part of a capstone design team last year where we actually designed this ground station that is on the roof of our engineering building right now, which is very awesome. And here is a 2-axis motor right here that is, all the cabling runs through the ground, and so you can control it from the inside of the building. And you can rotate this ground station, and there's the antenna right there to communicate. Now the problem is that you need to know where the CubeSat is at any point in time, and then based on the position of the satellite, compute an azimuth and an elevation to compute that. So Dr. Russ tells me that he found this software called gPredict. And gPredict is very good at taking orbital elements, or actually what's called a 2-line element. And so I went to Wikipedia because Dr. Russ said, hey, I need help with this 2-line element. Do you know what it is? And so here is a 2-line element of the International Space Station. And there's a bunch of numbers in it. But thankfully, the Wikipedia page kind of goes through and tells you every single thing that's in here. And so a lot of this is just like catalog number and when the launch was, what the Julian day is, things like that. But where my expertise comes in is the second part of the 2-line element, and it's the orbital element. So here's the inclination, the right ascension of the ascending node, the eccentricity, the argument of the perigee, the mean anomaly, and the mean motion is revolutions per day, which is basically like 1 divided by the period. The 24 hours divided by the period. And then the, some checksum things like that. And so what Dr. Russ needed was, hey, can you tell me the orbital elements of the satellite? Well, when the CubeSat was deployed, NASA sent a file like this. This is called an F1 file, NRC SD20 F1 file. And so basically what it does is it tells you the X, Y, and Z coordinates of the International Space Station at a certain point in time using the Earth-centered inertial frame. It even tells you the velocity, the ballistic coefficient, and some other parameters that don't really matter, like thermal coefficients and things like that. What I care about are these position vectors. Because what you can do is you can actually, using just pretty simple, let me see if I can find this, pretty simple orbital mechanics. And so here's a book that I use. So I teach spacecraft design this semester. And so here's a book written in the 70s called Fundamentals of Astrodynamics. And if you scroll over to, the end of chapter 1, and sorry, I should have prepared for this before, but it goes through, the energy of the system, the eccentricity, and then there's actually a section in the book, I think it starts with chapter 2, that basically says, here are all the classical orbital elements. So you've got the line of nodes, the right ascension of the ascending node, the argument of the perigee, the mean anomaly, the inclination, all of those orbital elements. And they actually have an example where they say, like, if you have position and velocity, how do you compute the orbital elements? And so I told Sam, I was like, all right, I can do this, no problem. So if you give me, once JagSat-1 is deployed, if you give me that state vector, and so this is an example CubeSat F1 file from 2020. It's not actually a CubeSat F1 file. It's actually the F1 file of the International Space Station. If you give me the position and velocity in the Earth-centered inertial frame, I will use this function called getOrbitalElements. And so, by the way, if you want to download this, so this is in my aerospace.git in a folder called satcoms, and then there's groundtrack.py, and I have a module called gpscoms.py. And so in here, if you go over to, get orbital elements, the equations from this textbook, R cross V to get the moment of inertia, the angular momentum, is right here. Here's the r vector, here's the velocity vector, and then here is r cross v to get the angular momentum. Then you do k hat crossed with that to get the line of nodes, and you keep going so on and so forth, and it computes all of the orbital elements. And so I got tasked with this 10 days before deployment. So Dr. Russ called me or emailed me and said, hey, we need to figure this out in 10 days. We're deploying in 10 days, and I don't want to miss the satellite. I want to make sure that we can communicate it with our ground station. And I said, oh boy, okay, here we go. So I went ahead and went through that book and wrote the code, and sure enough, the way the code works is it actually shows you the ground track over 24 hours. And you'll notice that, this is where we are in Mobile. This is where the satellite, or this example fictitious satellite is. And the blue line is the traverse, and the two red lines are basically like if you are within this black circle, which is spanned by those two red lines, if you are inside of it, you can see the satellite over your horizon. And so you'll notice that it's a little offset over 24 hours because the Earth is rotating. And so basically, every time the CubeSat goes by, eventually it will cross directly overhead of the of Mobile where we are. But it computes velocity here and things like that. And the end all be all is this. This is sort of what where we're going with this is that here's the initial position vector that they gave us. So the green ball is the Earth, and the blue line is the orbit. And so the yellow star is the coordinate that they gave me, and then the blue line is the Keplerian, the red line, which you can't see, is the Keplerian orbit, which is analytic. And then I actually, did a step further, and I actually numerically integrated the orbit using those initial conditions just to make sure that my Keplerian orbital elements matched Newtonian physics. So I did like a merger of two different kinds of mathematics. And that's all in the code that you can go and take a look at your leisure. And I plotted the perigee of the orbit here just to make sure that, again, everything lined up properly. And so, although this is a very, very cool graphic, Dr. Russ didn't necessarily care. What he did care about is, given this state vector, what are the orbital elements? So here are all the orbital elements, eccentricity, inclination, things like that. But then what is the two-line element? And so here is a two-line element. So you'll notice there are a lot of zeros in here. And the reason why, and some X's, is because that's all of like the catalog number and the launch year and things like that. And I knew Dr. Russ could do that himself. What really mattered was sort of the second line here, which is getting the orbital elements into the format that he needed with the right number of decimal places, the right number of spaces. And not only that, you, at least in this two-line element, you're not allowed to have like negative numbers for say like the right ascending node. Exactly, the right ascending node. So my code actually spit out like -3 initially, and I had to put an if statement that said in here, like, hey, it actually needs to be 356. And so you'll see here, like I have a print statement here, like, the mean anomaly must be greater than 180, and that's why it spits out, 298. Versus like the 113 or something like that. 75, I forget exactly what it was. And so there you go. So there's that two-line element. And so I gave this to Dr. Russ like 2 days before deployment, and he looked at it, made sure he could run it on his code. And then basically September 6th, I showed you the photo already. September 6th, we deployed. Okay, so that's not the photo there. Let's see. Let's go back here to, this is the photo that Dr. Russ sent me, and he was watching this live, 30 watching now, streaming 27 minutes ago. So he watched this live. He woke up at, and this is actually funny about time zones, is that Dr. Russ and everybody else, I would assume, the 30 people watching, understood that the satellite was going to be deployed at 9:05 Greenwich Mean Time. Well, for some reason, I thought that was Eastern Time. I didn't read the fine print. It was really early in the morning. And I was like, okay, cool. I'll log on at 8:05 or 8 o'clock a.m. Central Time, and everything will be fine. Well, it turns out I was 6 hours behind, and I missed it by 6 hours. And so I wasn't able to watch the live stream, but I was able to get photos and updates. And so here is the first CubeSat that you saw in that high-res image that Jessica Watkins took, and then our JagSat right here, and then that small little CubeSat over at the end. So then Dr. Russ got an F1 file from NASA and said, hey, this is a state vector that we think, it's an estimate that we think of your CubeSat. Keep in mind that aerodynamics are going to change things. What the NASA did is they took the state vector of the International Space Station and they added like a 2 meters per second delta V between those two, and they gave us an estimated F1 file. That F1 file has been updated since the time of the launch to the time of this video. But at the time when Dr. Russ called me, he said, hey, I got an F1 file. I need to work through some bugs. And so there were a couple bugs with the ballistic coefficient and the launch year and things like that we worked through and we fixed. And then Dr. Russ sent me this photo right here, which is the output of gpredict that basically shows two circles, very similar to that ground track photo, the image that I showed you in Python. And it basically says, if you are inside this first circle, you can see the ISS. And if you were inside this second circle, you can see JagSat. And so at the time of deployment, they were right over the Pacific Ocean, just west of South America. But you'll notice that those two circles are slightly offset. And again, that's because there was that 2 meters per second delta V between the two, which is awesome because the code that I basically took 6 days to write accurately predicted where our satellite was, which was like a very, very awesome, crucial moment in engineering. And then you'll notice the South Alabama is up here, and obviously we're not in the cone, so we can't see it yet. But later on throughout the day, we got a successful SatNogs. So Horacio Rosetta, so if you're watching this video, thank you so much. Eureka, data received 1 frame, JagSat-1. This is European, so that's September 7th, 2022. 2147 UTC. And it's awesome. Here is some raw data. It's all in hex. Dr. Russ has gone through and unpacked this. And so it's binary data, so I'm not exactly going to go through what all that is. Again, Dr. Russ was able to do that. But it's awesome because if you take the raw hex data and run it through a ASCII converter, you get a lot of non-printing characters, again, because it's binary, but you do get go Jags, right? Hopefully, I don't know which one the camera's mirrored. One of these is a J. Go Jags, and then tinyurl.com 2P8 4EZ72. So if you type in this tinyurl, you'll go to our JagSat page, and you'll see some more stuff about the satellite. So this is just an awesome end to 5-6 years of work. So many faculty working around the clock, so much simulation, so much code, so much math, so many students. I've got students who are in Washington, in Huntsville, in Atlanta, who have graduated and are so excited that, what they worked on is actually in space and going around the earth right now and transmitting data. This is raw data that came in. And so it's just really awesome to have a successful, build, or design, build, flight, ground test, trip through the atmosphere to the International Space Station, deployment, deploying the antennas and communicating with the ground station. That's just awesome that entire, V&V systems engineering design has come to an end. And now, we're not really come to an end. We're in operations and maintenance now. And so hopefully we'll get a lot of data from Dr. Spencer's time domain impedance probe and write a paper. So I hope you enjoyed this video. I was really excited about the fact that this worked. All that time and effort actually came into something that worked. And I hope you enjoyed it, and I'll see you in the next video.